My name is Jonah Flint, and this is my Physics 2212 Lab 5 report. In this lab, we are collecting data from a falling magnet in a conductive tube. We're modeling that falling magnet computationally, and then we are comparing that computational and actual model. For our findings, we found that the average fall time was about 0.724 seconds. With a magnetic dipole of 1.4875 am squared. The computational model expected a fall time of 0.435 seconds, and with a dipole of 2.166 am squared, it actually matched the observed model. Some key concepts are Faraday's law. It's just relating the surface integral of the electric field dotted with the change in length to the change in magnetic flux over time. And then we have the magnetic force equation on a wire loop, and Newton 3 and Ohm's law down here. For the system, we are using a falling magnet. For the surroundings, we have the aluminum tube and the earth. In our visual model here, we have F1 down here as the magnetic force on the loop, and F2 as the magnetic force by the loop, and basically we're stacking all of these loops to create the tube as the magnet falls through it. For our procedure, we first marked the north pole of the magnet. We then measured the mass of the magnet. Then we measured the aluminum tube, finding the inner radius, the wall thickness, and the length. Then we dropped the magnet 5 times and recorded to find the average results. Then we created a glow script model of the interaction, and finally we compared those two models. For the results, we have the average time through the tube at 0.724 seconds. The tube length was 0.46 meters. The width of the foil was 0.003 meters. The inner tube radius was 0.0135 meters. The magnetic dipole was 1.4875 am squared. And the magnet had a mass of 0.024 kilograms. Here we have our computational model. This is us just inputting those initial conditions I read off before. And down here we are doing the real work, finding the magnetic field, flux, and forces. Up here we're equating the two forces. Down here we're finding the B field, and here we are finding the magnetic flux as it changes in time. For our computational results, we found that, again, when we used the magnetic dipole moment we found in Lab 3 here, it did not match our observed results, but when we changed the magnetic dipole moment to 2.166 am squared, it did match our observed results. So for a discussion, just to reiterate, again, we realized that the magnetic dipole that we found in Lab 3 was inaccurate, and the actual magnetic dipole moment was 2.166 am squared. Some possible sources of error that could have thrown off this experiment are contact between the magnet and the tube as it fell, creating friction, air resistance, or some error in our measurements and timing. For the what ifs, what if the resistivity of the conductor were reduced as close to 0 as possible? How would that change the dynamics? The magnet would definitely fall slower. This is because a smaller resistance in the tube would lead to a greater induced current, and therefore a larger magnetic force. So the magnet would fall slower due to the greater force. And what if holes were cut in the tube? How would that change, affect the rings in the model? If the holes were cut into the tube, that would reduce the induced current, and therefore the magnetic force, thus the magnet would fall faster. Thank you very much.